In this video, we will recap some essential math concepts and notations that will help us better understand backpropagation. At the core of backpropagation are derivatives. Our usual way of writing a derivative is with a bar next to a function. So we say, for example, f prime of x, or shorthand y prime. This notation is great for normal derivatives, where our function only depends on one variable. But if we're dealing with multiple variables, which is certainly the case for neural networks, so for example, we have the function g of x1 and x2, then the prime does not tell us whether we should take the derivative with respect to x1 or x2. To solve this issue, we switch to the Leibniz notation, where we explicitly denote which variable we derive by. And so we write d, then our function, and then dx, the variable we derive by. To give you some intuition what dx and dy stand for, we can imagine a function. And then our dx is a shift along the x-axis, and dy is the resulting shift of our function into the y direction. And what is now important is that this expression here does not just capture this ratio here, but instead the limit of this ratio. And what is meant by the limit is that dx approaches 0. So our change gets very small, and as the change gets very small, we approach this tangent line here that represents the derivative. And the derivative in its essence is then how changing our x affects the function. Now let's get back to our multivariable function. Here we have to be a bit careful, because it is convention to not use the d, but instead the partial d. And that is because when we have multivariable functions, we take not just normal derivatives, but partial derivatives. And so what this partial d signalizes is that there's more to our function than just a single variable. So when we then write partial d, our function g, and then whatever variable we want to derive by, so let's say x1, we know that then our g has also other variables that we could take the partial derivative from. To give you some intuition for a partial derivative, we can again imagine a function, this time depending on x1 and also x2, and it will result in, let's say, x3, which we can also imagine as a height. And what this gives us then is some kind of surface, so maybe like this. And now the partial derivative at a certain point, let's pick this point here, is then how steep the surface is in that direction. So if we have here the partial derivative with respect to x1, we look in the direction of x1 and note then this slope. The same would go for a partial derivative with respect to x2. This is done maybe at this point here, and then the change here is rather mellow, so let's go with that here. And we can do that for every point. So maybe here, again with respect to x1, so it goes in this direction. And let's draw the arrow in proportion to the change, so it's rather small. Here it goes maybe uphill. Here again rather small. Here also rather small, maybe here a bit steeper, and so on. And this already looks like a field of vectors. And on this topic, we can jump to the Nabla operator. And the Nabla operator writes like this, and it looks like this. Not to be confused with this operator here, which indicates change. And you may remember the difference between them by looking at the bottom side. So here we have 2 points, and for change we always need 2 points. And the Nabla operator relates to derivatives, and we often take derivatives with respect to 1 point. So that might help you remember. Now, what is the Nabla operator? The Nabla operator is a vector of partial derivative operators. Now, if we go back to our partial derivatives here, if we split the partial derivative here into operator and function, we have simply our partial d divided by partial d and then the variable we derived by. This is now the operator, and then the function. And combined, we get a partial derivative. So the Nabla operator encapsulates these partial derivatives and all of them. So we write generally partial d divided by partial d x1, then partial d divided by partial d x2, and so on, generally until partial d divided by partial d xn. Normally this is a column vector, but let's ignore it for now. And if we now apply this Nabla operator to a function, we get the gradient of this function. And so what this looks like is that we just plug in the g for our partial derivative operators. So here goes our g, and we have only x1 and x2, so it's rather short. And now what can we do with this gradient? If we apply the gradient of a function to a certain point, so we can go back to our surface here. And since we now have the partial derivative in all directions, we actually get a proper vector field. So now let's imagine at that point here, we are not restricted to x1 or x2, but we get the proper slope. Maybe that's that here. And here maybe it goes in that direction, and maybe here it was actually a bit to the left, and so on. Now, one final use case of the Leibniz notation is the application of the chain rule. So let's imagine we have a nested function, maybe f1 of f2 of f3 of x. And if we now want to take the derivative, we write dy divided by dx, d normal d, since we only have one variable. And then on the right side, we have to now remember the chain rule. So we start with the outer function and take the derivative with respect to the inner part. So that part here. So we write df1 divided by df2. And we don't have to write the f2 part in its full form, since we know what the f2 represents from here. Then the next part of the chain rule is to multiply with the derivative of the inner part, so f2. f2 is again a nested function, so we first take the derivative of the outer part with respect to the inner part, and then multiply with the derivative of the inner part. And here finally we can take the derivative with respect to our x. And as you can see here, we derive by several different things, and so the Leibniz notation is very useful to make this neat and tidy. Of course, it's not solved at this stage, but now we can solve each of these derivatives individually.